Good day. Welcome to the Cool Phys channel. Today I will talk about what is known as the skin effect. Okay, and I'm going to do the derivations for this effect. And I'm going to use, so it's going to be a different derivation from the usual one that you might encounter in a graduate electrodynamics course, because I'm going to use integral representations of Maxwell equations. Okay, so the integral representations is the key here. Okay, and what I'm going to actually end up doing is I'm going to derive the Bessel function, okay, rather than invoke the use of the Bessel functions. Okay, so let us think about what is the problem first. So basically you have a wire. Okay, so skin effect. Actually, this is skin effect in a cylindrical wire. So this is important. Our wire is cylindrical. That's why you can use the Bessel functions. Okay. So what is the problem? So basically the issue is that we have a wire. This is our wire. And we run, so I'm going to call this the Z direction. So my coordinates are going to be, of course, Z, rho, and phi. And we run a current in the Z direction, and we assume that the time dependence of this current is harmonic. So let us say e to the I omega t, sorry. So this is a harmonic time dependence, okay? We're also going to assume that our system, the wire, is conducting, okay? And it's a good conductor. That's going to make our life a little bit simpler. Okay, so the wire is a good conductor. Okay, so let us analyze the geometry here, because we want to set up our integral representations of the Maxwell equations, and we need, of course, surfaces for that. Okay, so let me draw a bigger example of the wire. Okay, and one. Okay, so we're going to take one surface to be, I'm going to call this S1. Okay, and C1 is the contour around it. Okay, so we're going to go around this surface eventually and have a contour like so. That's going to be, so I have two surfaces, S1, and then here's the axis, okay? And I'm going to also take along the axis another surface. Okay, maybe I will go around this contour like this. So that's surface S2. Okay, so those are the two surfaces that I'm going to use. Okay, so here you just have the axis of the cylinder. I didn't draw it quite perpendicular. I apologize for that. Okay, now what are the Maxwell equations that you're going to use? First, I'm going to write them in differential form. Okay, so first of all, you have that the curl of what? The curl of D. Okay, we start with the curl of H, actually. Okay, so the curl of H is equal to the free current, right? The free current, yeah, free current plus the displacement current. Okay, so we have these. That's one Maxwell equation. The other Maxwell equation we have is that the curl of E is equal to minus the time derivative of B. Okay, so this actually is ampere. Sorry, ampere, and this here is Faraday. Okay, and then we need, so these are the Maxwell equations that we will use, and then we need the so-called constitutive relations. which have to do with the nature of the material that we are using. Okay, so the constitutive relations are actually, the way they go is that D is equal to epsilon times E. And I think since we are in a metal, we actually, this is just epsilon 0. And then we also have that H is equal, mu 0 times H is equal to B. And the only really non-trivial one is Ohm's law, which relates the current and the electric field. Okay, and on top of this, we have a harmonic time dependence. Okay, so we can actually rewrite. So actually, I'm going to rewrite these equations. So I'm going to say curl. Let me proceed like this. I'm going to rewrite the first one as mu 0 times J plus, well, I'm going to write here, first of all, that this is epsilon 0 E, but I'm also going to use the time dependence. So I omega, it would be I omega, that's the harmonic time dependence, because recall that D field is D something time independent times I omega t. So if I take the time derivative of this, I just get multiplication by I omega. Well, I put a mu 0 here, so I should do that. And I would have E, right? I would have E, epsilon 0 times E rather. But instead of E, since here I have a J, I want to narrow it down to as many vector variables as possible. So I'm going to say J divided by sigma. Okay, and then my other equation is, so that's one equation I have. And my other equation is that the curl, and I'm going to say J. Okay, so this is actually J over sigma, but I'm going to bring the sigma over to the other side. So that's actually minus I omega sigma times B. Okay, so these are my Maxwell equations. And there's one other thing I will do, namely that if we have a good conductor, then sigma is large. Okay, so I can actually get rid of this. So I basically have a standard amperes type current, although it's by nature of this material. So we have a standard ampere type current. Okay, and these are my two equations, which I could in principle combine into a wave equation, but I want to do it. This solution is different from the usual type, so I'm going to do it via integral Maxwell equations, and I'm going to use surface 1 and surface 2. Okay, so let's focus on surface 1. Okay, and this is the equation that we will use for surface 1, because we should actually analyze that a bit. So we can, of course, infer that the current flows in the z direction. Okay, which also means, because of Ohm's law, that the electric field would be in the z direction. Okay, but you know this, you have some feel for, based on Ampere's law, you have some feel for what that would mean for the magnetic field. Okay, so for the B field, magnetic field, you would have a magnetic field in the phi direction. Okay, so so we're going to use this particular surface and our integral Maxwell equation. So we'll keep this slide around. Okay, the first integral Maxwell equation is, of course, integral around the circle, and it's going to be B phi. We only need the phi component because we're going around. So we're going around this circle. Now this circle has to have some radius, which I'm going to call rho. Okay, so this circle has some radius rho. Okay. Anyway, for now I'm just going to integrate. So this is going. If I do this line integral, I'm just going to have rho times d phi on that side. Okay, and then I need mu 0 times the surface integral. So this is C1 contour, this is S1. So just to show you, this is one, we are doing this equation, and over this surface, this is going to be a kind of like a flux, so amount of current. J is current density, so this is going to be the current flowing through that surface. Okay, so this is going to be J dot ds, and we can actually write this as b phi, which depends on rho, 2 pi rho, and that's equal. Well, what is it going to equal? Well, we have to, J flows in the z direction, so it's normal to the surface. Okay, so that's easy. So it's going to be mu 0 integral jz rho. Okay, and it's going rho prime rather. Okay, and we're going to integrate from 0 to rho, and it's going to be rho d rho prime. Okay, but then of course we have to also integrate in the phi direction, and that gives us a factor of 2 pi. Okay, so the 2 pi's cancel, and our first equation is that b phi rho is equal to mu 0 divided by rho, integral from 0 to rho, jz rho prime d rho prime. Okay, so that's one equation. You can underline this. Okay, now we want to do another equation, and another equation is this one, but we're going to use surface 2 for that one. Okay, so the curl. So we are using Stokes' theorem here. Keep in mind. Okay, so this first thing that I did here, this was we used Stokes' theorem, i.e., if I integrate over this surface, and this is the curl of a vector field, then I get the line integral around this the contour. Okay, so this was really, I should make a mark of this. So this, what I used here, is the Stokes' theorem. Okay. So let us do the other one. Okay, so curl of J, again I use Stokes' theorem, and I go around this contour. If I go around that contour, and well, I have to give this some direction, right? So I have to get dimensions. So I'm going to give this distance the dimension rho, okay, and this distance I will give it some delta z dimension. Okay, so what is going on here? If I apply Stokes' theorem, okay, so I'm going to integrate around this contour. So I'm going to go in the direction of what I assume the direction of the current to be. So I'm going to have along the axis jz0 delta z. Okay, now here I'm going in a direction which is perpendicular to the current. Okay, so my loop integral doesn't give me a the contribution. Let me just remind us that what I'm doing is this loop integral. Okay, so this loop integral around the loop defined by this rectangle. Okay, so I had one contribution which I already wrote down, which is j0 delta z. Here I'm going, but the direction of my loop is perpendicular to current, no contribution either from here nor from here. But I'm going to have this back integral, which is minus jz rho delta z. Okay, so I took care of the loop integral. Okay, and now I have to also integrate the flux. So I'm going to have, on the other side, I have minus I omega sigma, and the magnetic flux over, let's say I'm going to write A, and over the surface S2. Okay, so I need the magnetic flux over that surface, and that magnetic flux is going to be the integral. Okay, so nothing is changing in the z direction, so I can bring that dependence out. So I'm just working on the integral here. It's going to be delta z integral 0 to rho b phi rho d rho, and this has to be primed. Okay, so we see that if we write this in here, then the delta z's cancel. Okay, and what we have is jz0 minus jz rho is equal to minus I omega sigma 0 to rho b phi rho prime d rho prime. Okay, so this is our second equation that we use. So let's just think about this a little bit. Okay, so basically, when I did this second integral, okay, so I was using, of course, Stokes theorem again, but I was also using the fact that the magnetic field, okay, so it penetrates this in the phi direction, and that's the normal direction to this surface. Okay, so the magnetic fields, they go around in circles, so they penetrate in the phi direction, and they are normal to the surface. Okay, so that makes my integration and so forth easier. Okay. Okay, I want to rewrite this. I'm going to write jz rho is equal to jz0 plus I omega sigma 0 to rho b phi rho prime d rho prime. Okay, so this is one equation, and here's my second equation. Now I'm going to put them together. Okay, so what I'm going to do is I'm going to, for example, I want the current. Okay, but if I have the current, I have everything else. I will show you why that is. But I'm going to take this b phi rho that I found here. I'm going to substitute it in here. Okay, and then we're going to solve it. So that's going to be one integral equation for the current. Let's see how that is. So I have j z rho is equal to, sorry, j z 0 plus I omega sigma 0 to rho. I have here d rho prime, but now I have to write b phi rho. Okay, now I have to write my b phi rho here. I'm going to write that from this equation. Okay, so I'm going to put my mu 0 constant out. There's a 1 over rho, but that's now a rho prime. Okay, so that's there. And now I can write 0 to rho prime, jz rho prime prime, rho prime prime, d rho prime prime. Okay, so that's my equation. Okay, so this is my equation now. Okay, and this is just something that I mistook. So jz rho is equal to jz0 plus I omega sigma mu 0. And then we have an integral, sorry for not writing it too clearly, from 0 to rho, d rho prime over rho prime. Within that, another integral from 0 to rho prime, jz rho prime prime, rho prime prime, d rho prime. Okay, so this is an integral equation for jz rho. Let's write that. And we're going to solve this. So this is the integral equation for jz rho. Okay, and now if we have jz rho, we also have E, right? So we have this constitutive relation according to which if we have jz rho, we have E, okay? And if we have jz rho, we can also get B, okay, from Ampere's law. Okay, so if you have jz rho, you have everything. Okay, and now successive approximations. Okay, so how does that work? So how to solve this integral equation? That's the next issue. But before I go there, let me just make one remark, because this is important. So here we have current, here we have current density. Here we have I omega sigma mu 0, okay? And here I have current density, but that current density is multiplied by distance, and divided by distance, okay? So so actually this integral has units of current density times distance squared, okay? Current density times distance squared. Because I didn't write this very nicely. I'm sorry about that. But the point is that mu 0 omega sigma has to have units of inverse length squared. Okay, and the way that's normally done is that delta is equal to square root of 2 over mu 0 omega sigma. That's usually taken to be the skin depth. Okay, and you will see that this parameter delta, so now we can rewrite our equation in terms of that parameter delta, but this parameter delta is it's going to define the behavior of the current. Okay, so it's going to be the length scale that defines how the current behaves as a function of rho. Okay, so let us rewrite our equation. So Jz rho, what do we have? It is equal to Jz0 plus 2I over delta squared. And then I have my integral 0 to rho d rho prime over rho prime. And then I have another integral from 0 to rho prime, Jz rho prime prime. And this has a rho prime prime d rho prime prime. Okay, and now we're going to use the idea of successive approximations. And our first, so basically the successive approximation method, the way it works is you take a first guess. And our first guess is going to be constant. Okay, so let's take the first guess that our current J0 is a constant. Okay, and from this first guess, we are going to able to take the, so this is actually our 0th order guess, really, okay? And we make successive guesses, we calculate successive guesses to our current based on this first guess, okay? So in other words, our current is actually going to be a linear combination or a sum, okay, of a 0th order approximation plus a, well, I'm going to call it first order approximation and so forth, okay? And this, I already told you that this 0th order one is the constant J0. How do we get the first order approximation? The way we get the first order approximation is Jz1 rho, okay? And if Jz1 rho, we get it from the 0th order approximation the following way. So 2I over delta squared, 0 to rho, d rho prime over rho prime, integral 0 to rho prime, Jz rho prime prime, rho prime prime, d rho prime prime. Sorry, what I should have placed here is our 0th order approximation. So this will give us the first order one. Okay, so and this is an easy integral to do. Okay, so that's so if Jz is a constant, then we basically have 2I, J0 rather is a constant divided by delta squared, and then we just have to integrate this. So the first integral in rho prime is if we integrate 0 to rho prime prime d rho prime prime, that's going to give us that first integral. That of course gives us, so 0 to rho prime prime d rho prime prime, that gives us rho prime squared over 2. Then we divide by rho prime, so this is rho prime over 2, and integrate again. So in the end, we'll go, so that second integral is the 0 to rho. We divide by rho prime, which we have this rho prime, we divide by this one. So it's rho prime over 2, but it's easy to see that that's actually rho squared over 4. So this is rho squared, but I'm going to purposely write 2 times 2 on purpose. Okay, and I'm going to take this and raise this to the first power. Okay, so up to what I called first order, but it's really second order in rho. Okay, so be careful, it's second order in rho. But up to first order, my Jz rho is J0 plus, actually, I can write it like this. I can take that the J0 from here, and it's actually 1, right? 1 plus 2I over delta squared times rho squared over 2 times 2. Okay, and now we can keep going. So we're up to here now, but we can keep going because if we now put this in as a solution, okay, then we have to integrate this approximation to get the next term in the series. Okay, so in other words, the next thing that we will have to do to get what I'm calling the second order solution is to say, I'm going to say that this is 2I over delta squared, 0 to rho, d rho prime over rho prime, integral 0 to rho prime. But here I'm going to put the first order correction. Okay, and that first order correction is 2I over delta squared J0 rho prime prime squared divided by 2 times 2. And I have my rho prime prime d rho prime prime. Okay, so here I put JZ rho. I guess it was a function of rho prime prime. That's what I put here. Okay, so this is what we mean by successive approximations. Okay, so what do we get here? Okay, first of all, we're going to get a J0. Okay, that's not too surprising. And then we'll have 2I divided by delta squared, but we have one here and one here. That's squared. Okay, and then we still have to do our integral. Let me take out of the integral the 1 divided by 2 times 2. Okay, and what we're going to be left with is the integral 0 to rho prime d rho prime. No, sorry, that's divided by rho prime. Okay, that and then I'm going to have my integral 0 to rho prime. And here I already took everything out. I'm just left with rho prime prime to the third d rho prime prime. Okay, and so now we do this integral. That's the next. Okay, so first we have to do this integral. That gives us a rho prime to the fourth divided by 4. And then we divide by rho prime. Okay, so one last integral we're going to have is it's going to be rho prime to the third because we divide by rho prime, d rho prime, but there's that 4 there. So we're going to get rho to the fourth divided by 4 times 4. Okay, so our second order correction turns out to be J0 2I over delta squared 1 over 2 times 2 and times 1 over 4 times 4 rho to the fourth. Okay, so that's our second order correction. And you can guess the pattern, okay? So it's going to be 6 times 6. Once we put here, so you can easily guess that the next term, we're going to integrate rho to the 4, but the rho to the 4 will be multiplied by rho prime. So our integral will give us, it's going to be an integral rho prime prime to the 5th. So it's going to be rho prime to the 6th over 6, okay? Then we divide that again by rho prime. So it's rho prime to the 5th over 6. But when we do the integral, it's going to be rho to the 6th over 6 times 6. Okay, so we can guess the pattern. And I will write the solution to the problem. Okay, so the overall solution is, so let me title this slide. This is the solution is J0, then a sum, and let this sum go from 0 to infinity, okay? And we're going to have 2I over delta squared to the power n, okay? But then I have to, sorry, of course, we're going to have rho to the 2n, okay? And what about these guys? Well, with these guys, I can do something. Okay, so these are actually factorials, but they're funny factorials, right? So recall that it goes 2 times 2 times 4 times 4. The next one would be 6 times 6. So basically, I can take a factor of 2 out of each. Okay, so if I take a factor of, for example, this is, I'm going to take 4 factors of 2 out of this one, 2 to the 2n, n is 2 in this case. Okay, and times n factorial squared will do it. Okay, so so the final solution ends up being 2 times 2 to the n times n factorial squared. Okay, and it turns out that this can be written in terms of a Bessel function, because of course, if you look at our original equation, okay, so which was something like, well, we can go back to it. So let me just fill you in on that, that the other way to solve it, okay? So there's this other way to solve it. So here you have curl of J related to curl of B, and you also have curl of B related no, sorry, curl of J is related. So let me write those equations again. So you could solve it another way, okay? So if you have mu 0 J, I'm not going to solve it, I'm just going to outline this, minus I omega sigma B, okay? So you can take you can take the curl of, for example, this one, okay, which means you have to take the curl of B here. So your curl J ends up being minus I omega sigma mu 0 J, right? And then you can say this curl is gradient divergence of J, but the divergence of J, you assume that is 0. And then you're going to have minus Laplacian J. Okay, and if you put those two together, you're getting that you have a three-dimensional Laplacian equation, and this is actually I omega mu 0 sigma J, and this is a wave equation. Okay, and if your situation is cylindrical, then it's obvious that you need some type of Bessel function to solve it. It turns out that this solution that we derived here, not using the differential forms of the Maxwell equations at all, this solution that we derived here is actually a Bessel function. Okay, so you can check that. So yes, that's one last thing I wanted to say about this. Okay, well, thank you very much for your attention, and I hope you found this little derivation for the skin effect useful. Thank you. Bye bye.